Actually need to set up my screen here. Let's see. I just need to share my screen. Feel free to say hello in the chat if you're online. It's going to be a shorter stream today. I'm in London and I'm here working with Lewis on the ARC prize. And I'm going to be going back to Ireland soon. Been in London a good bit. Actually going to an MLST event tonight, Machine Learning Street Talk. Good channel on, hey Yugi, good channel on YouTube with Tim. Has interviewed a lot of the winners from ARC in the past. And finally, I figured out where my share screen button is. And okay, it's going to maybe do Windows for a second. And I've just done one computer today, so it's going to be a little bit harder for me to see things. But yeah, I wanted to talk a little bit about kind of news, reviewing Simon Wilson's blog, but also I wanted to talk a bit about this list of papers that Ilya Sutskever apparently gave to John Carmack. Now, it's not like John Carmack, who wrote Dune and is a well-known programmer. It's not like he published the list of papers you should read, but so I don't know what the truth of this story is. But if you dig it up, you can find a few things online, a few lists of these papers. They're machine learning papers that apparently Ilya Sutskever recommended people read. And if you read this, then you've understood maybe 90% of what's important. Interestingly, it's not all papers. There are quite a few blogs that are listed here. And I was kind of hoping some of them would be old, but it turns out quite a few of them are relatively recent. But that, I suppose, makes sense given Transformers are quite recent. And I've started to try and read one every day. I don't know if I'll be able to keep up with that, but I've kind of skimmed 3 in the last 2 days. So I'm at a good rate so far. And let me just quickly check here if there are any comments. I'm going to show you a few things. So the ones I've looked at so far, first one is this blog on LSTM, long short-term memory networks. At least I think that's what it stands for. Not really talked about so much since we have Transformers now, but kind of a precursor to Transformers. And what's interesting is if you go right down, you can see, and notice what the blog year is. It's 2015. So this is before even OpenAI existed. But you can scroll down here and you can see a section where there are some hints at what might be useful. And if you just search for the word attention, you can see right here. Look at this. This is 2015. LSTMs were a big step. It's natural to wonder, is there another big step? A common opinion among researchers is yes, there's the next step and it's attention. The idea is to let every step of an RNN pick up information from some larger collection of information. And it talks about an image where you can attend to other parts of the image. And there are a number of really exciting results using attention, and it seems a lot more to come around the corner. So that's pretty interesting. 2015, and clearly if you were in machine learning, which I wasn't, I was working on desalination and specialty separations at that time, but clearly attention was known as an interesting idea. And yeah, you can see here, actually on this blog, you've got, thanks to Ilya Sutskever, you've also got Dario A. Modi, who's the CEO of Anthropic, who was thanked here by the author. And I was thinking, yeah, who is the author? C-O-L-A-H. And so I went to the About page, and this is Christopher Olah, who I didn't know about. But yeah, it turns out he's one of the co-founders of Anthropic. So that was pretty interesting. And yeah, I'd kind of known what these long short-term memory neural networks were, although I've never trained a model on them. And the idea is that they're an advancement on what's called a recurrent network being where you have one, say, neural net, and you keep feeding the output back around and you run it multiple times. So here, if you unroll the recurrent network, now this is exactly the same set of weights here. It's kind of showing you if you run the same network multiple times in an unrolled way, this is what you have. Now, these are a real pain to train because when you backpropagate, you have to kind of unroll the network like this in order to backpropagate fully through it. Whereas the nice thing in a transformer is you can just do a forward pass and back propagate. So this was kind of one of the problems with recurrent networks. But another problem with recurrent networks is because you keep on writing back into the same set of activations, you kind of overwrite the history of information that was there very easily. So if you have a sentence, and remember, there's no not remember, but know that in a recurrent network, you don't have the ability to attend to all of the previous sentence on the same forward pass. What you're doing is forward passing on the first word, then on the next word, then the next word. So if you were forward passing on this sentence here, you would forward pass, forward pass, forward pass. You're not, when you're forward passing on network, you've no direct access to these words here. You only have what is stored in the activations within this neural net here. And yeah, basically you overwrite a lot of the information when you operate recurrently. And that means you tend to lose. So even though you might have initially forward passed it on the word unrolled, by the time you get to network, that state of unrolled is just completely overwritten here within the activations you have. And so yeah, LSTM was kind of an improvement on these recurrent networks. And the improvement is, well, if I'm overwriting here in a bad way, why don't I make the architecture so I can specifically decide what parts to overwrite and what parts not to overwrite? And that's the idea with the LSTM, which basically separates things up. It's kind of hard to see here. Try and zoom in. Let me see if I have any comments. Sorry, this is hard because I'm on one screen. Hey, Raja. So instead of just always writing back to the state, what you do is you keep some percentage of what of the input here. So you can think of this as your state that's flowing along the top, and you're going to keep some percentage of that state. So this is the amount that you want to remember. Here you're going to calculate the output, and you're going to also write some portion of that output into this state that is passed from one recurrent pass to the next. So whereas in a simple recurrent network, you're kind of at risk of overriding stuff that's important. In the LSTM, I'm not describing this in a high level of detail, but basically you split different portions so that you have a remember portion, you have a forget portion, and then you have an update portion. So yeah, I mean, if you think about information, let's say I have a state, it's a container, might be a container of food. Some of that food I want to keep, some of it I want to discard, and then I want to add in something as well. Maybe recipe is a better analogy. I want to keep some, I want to discard some, and I want to add some. That's broadly what we're doing here. Here's what we're adding in from the new input. Here's what we're remembering. Here's what we're forgetting. This is loosely what an LSTM is trying to do. And it turns out this allows you to have long-term memory. You can train models to correctly remember and correctly forget the right pieces. Now, of course, since then, it seems like transformers do this even better because they explicitly attend to everything in the past. So nice blog here from Christopher Ola. Now, there are two other ones I looked at. There's this one here on minimum description length, which is by Jeffrey Hinton, also well known. And I actually haven't finished reading this, but I'll give you one of my takeaways so far, which is this thing around minimum description length. So let's just let's go here and think about very high level some data. If you have some data and you want to train some model to represent that data, let's consider data as simple as this series of twos and fives. So 2 5 2 5 2 5, like this. And let's say we want to have a model to represent that. Now, because there's a pattern, we could write a program. The program would be repeat 2 5 however many times. What's that? 1 2 3 4 5 6 7 8 9 times. So this is a program here that describes this snippet of data. This is my program. This is my raw data. And I hope everyone can hear me there, by the way. Let me check. If you can't, let me know. So I have some raw data. The idea of the program is to represent that. And then the way you can say whether the program is compressing it is, well, this is the minimum description length, this concept, minimum description length. And the minimum description length is the length of the program plus the residual. And the residual is basically what the program doesn't describe. And basically, if you think of a large language model, what you're trying to do is kind of represent all of the raw training data the language model is trained on. And you're trying to do it in a way that's ideally more compressed. So ideally, the length of the program, which for a language model here would be the bits required for the weights of the model. And then, I don't know, you could think about some residual, which you could think of as maybe cross entropy loss, the difference between the ground truth data and then what the model predicts. I don't know if this is exactly accurate, so I'm going to put a little tilde here. We'll say X entropy loss. And you find this concept of minimum description popping up a lot in machine learning. And it's kind of the idea that what matters is having a short program and having a program that will be as accurate as possible so that this residual here is small. Now, you can always write a program that's perfectly accurate just by using the raw data. I mean, a program that would be perfectly accurate would simply be like print that string. I guess that would be a perfectly accurate program, but it's not shortening anything because you're literally printing the full length of the data. So you can always write a program that doesn't shorten the data, but the goal is, if the data is indeed compressible, the goal is to write a program that is more succinct such that the residual is, you have to pass a smaller residual. Like in this program here, there is no residual because I'm exactly describing this data. When I have a program repeat 25 9 times, that's perfectly describing this string here. So there's no residual. So the program is ideally shortening the number of bits to represent this raw data. And there's a link here because where I'm going with this is there's actually a link with what's called weight decay when you train a language model. So when you train a model, you'll all be familiar with minimizing the cross entropy loss. So often if you have a transformer, you'll often want to minimize the cross entropy loss, which is the difference between the ground truths and the predicted outputs. And normally what you do is you run an optimization process to adjust the weights, the LLM weights, to minimize the cross entropy loss. And when you do the optimization, you often will use something called stochastic gradient descent. So gradient descent is one approach, kind of a Newton-based approach, where basically you have a surface. You can imagine this large dimensional surface, and you want to get to the bottom, which is hopefully the minimum of the cross entropy loss. And to get to the bottom, you look at where you currently are, maybe here, you see what the slope is, and then you follow that slope for a step. You follow a step down the slope, and hopefully it brings you eventually to the minimum. And when you're at the minimum, then your model is hopefully converged. So this would be a simple approach where you just follow standard gradient descent. You get to the bottom, which is good. But there's a better approach that is called ADAM. And the reason it's called ADAM, by the way, is because it's adaptive momentum. And ADAM introduces a few things. ADAM, first of all, it will not just follow the gradient, but it will also build up momentum. So if it sees that the optimization is moving along that curve from step to step, it's moving along smoothly, it's going to increase the momentum term, and it's going to kind of accelerate. So when it's moving smoothly, it's going to accelerate. There's also a piece of the ADAM optimizer where when it sees noise, like if in going down to the bottom of that bowl, the surface is very jagged, it'll actually see a variance in the gradients and slow down. So ADAM is an adaptive optimizer, and it converges faster because of momentum, which allows it to accelerate, and because when the surface is very bumpy, it actually slows down. And this allows large language models to converge a lot better than using something like gradient descent. Let me just check here for comments again. think we're doing fine. 24 on a stream, pretty great. Thanks for joining, folks. It is available after as well. So the way that this went is there's gradient descent. You can optimize the language model. Atom optimizer is better. But what's even better is Atom W, which is Atom, but with weight decay. And what Atom with weight decay does is every step, it looks at not just the cross entropy. So it's not just minimizing the cross entropy. It will also minimize plus a weight decay term that is bigger when weights are bigger. It could be like the square of the weights. And what this encourages is it encourages small weights. And empirically, this works very well. If you add the weight decay, rather than having some very large weights that are optimal, it will encourage the weights to be small and bring you to the minimum. So small weights and the minimum, that's Atom W. And here's where I'm going to bring it all back to this paper, which is actually, it turns out there's a theoretical basis for why you would minimize cross entropy and you would minimize this weight decay term. And that theoretical basis can be expressed in terms of the model, the minimum description length, because if you go all the way back here to minimum description length being the length of the program, you can think of the length of the program as the bits required for the weight of the model. And then, yeah, the residual is what the program, where am I going with this? Well, let's just go to the paper actually. And let's scroll down because it has the equation written. Yeah, basically here. So you have a weight decay term. This is actually like, this is weight decay because you've got the size of the weights. And then you've got here, you've got the cross entropy term essentially. So you're trying to minimize the total description length of the data and the weights by minimizing the sum of the two terms. So you kind of come back around, and what you find is that if you minimize the description length, it ends up being equivalent to doing weight decay. So yeah, I thought this was kind of interesting, and it gives a justification for why weight decay should be in there. And there's actually another implication. I'm not going to explain this very well, but basically weight decay makes sense if your weights are kind of real numbers or very high precision numbers. So if you have a float 16 number or a brain float weight, but if you are using quantized weights, which is popular now, like if you look at the GPT OSS model, so if we go to Hugging Face and we go to the OSS model, this is actually trained in 4 bits. So you've got MXFP4. So most of the weights, I think it's the weights in the multi-layer perceptrons, not the attention, but they're 4-bit weights. And when they're 4-bit weights, it means they're only able to take certain quantized values. And what this does is it provides regularization. It forces actually a shorter description length already. And because you're already forcing the description length, it turns out probably you don't need as much weight decay if you're training these quantized models, because you're already forcing a shorter minimum description length by forcing it to be quantized. So yeah, this is not something deeply discussed in the paper, but maybe it's something people or maybe OpenAI are thinking about. I wonder if they used a different weight decay term, but in principle, I think you should be using a smaller weight decay if you're going to quantize the model, because you're already getting some regularization that wouldn't be there if you were using higher precision weights. So yeah, anyway, loose thought. I'll put some links. Actually, you can all just find this yourselves. I'll put it in the chat here. DZYIM. I don't actually know who that is, but they've compiled this nice list here. So let me throw it in the chat. And you should see it pop up. There is one other paper, I'll talk about it next week, which links, that's kind of minimum description length. But if you're trying to compress data, if data is compressible, then there are going to be patterns in that data. And those two ideas are linked. The fact that data has got patterns means that it's not random. And the fact that data is compressible also means that it's not random. If data is completely random, then it's not compressible. There is no way to compress some string. Like if I just write a string here, where am I? If I write a string of numbers, something like this here, that's probably not completely random, but there is no way to compress this if it's purely random because there is no pattern. So you require patterns for it to be compressible. So these two things are linked: compressibility and the existence of patterns. And apparently that, to show it formally, is not trivial, but it is shown in one of these papers here. It's actually this one here, I think, Kolmogorov complexity and algorithmic randomness. Look at how many, though, here are linked to minimum description length. Another one on minimum description length. Let's see if I can even just search for minimum. Okay, maybe that's the only one with it in the title, but clearly it's there more often. Let's see if I can find the paper. Oh, this is a book, is it? Yeah, I have to say that's not what I expected. Maybe it is a book, but it's also a paper. No, that's a different. That's for qubits. Wow, we're getting into quantum. Let's see if we can find the paper. See how many times random. I think it was that paper. Why can't I find it? Oh, this one here. It's by Steinitz, who I believe is famous, although it just shows you I haven't read a book enough about machine learning. But yeah, we'll look at the abstract. The paper is very difficult to understand. It's a lot of maths, but it provides a minimum introduction to algorithmic randomness, linking two concepts: one randomness and Martin Luff randomness. And okay, the KC theorem, more general notion of information content. And then we build two natural definitions of randomness for infinite strings and prove their equivalence. So yeah, this is quite a lot of maths in this paper to show that there are two equivalent ways of thinking of randomness. One is that stuff is not compressible. If it's purely random, there is no way to compress it. But also, if it's random, there are no patterns. And the fact that there are no patterns and it's not compressible, those end up being equivalent. So that's what this paper kind of shows. I think the first few paragraphs are kind of readable, maybe the first few pages even, but it does get pretty mathsy after that. Well, why is this interesting? It's interesting because we want to know how to write short programs that describe our data well. That is the problem of machine learning: writing short programs that describe data well and that don't overfit. And that constraint of having to keep them short, that helps us to avoid overfitting. And you can see the analogy: if you now force yourself to use quantized weights, that forces things to be short, provides regularization, avoids overfitting. So these ideas are linked. And it's also something in the ARC challenge, ARC prize, which I'm working on with Lewis. We're always thinking about how can we write shorter programs, or how can we develop measures of shortness or conciseness or low numbers of bits, because those are programs that tend to be more efficient in terms of describing the data, because they reduce the program length plus the residual that's required. The residual being how inaccurate the base program is. So I'm actually going to wrap up fairly early here. If you have any quick questions, let me know. I'll be on for a longer session next week. Let me head back over to here, and I'll stop sharing my screen. Nice. I got the feed. We probably will share a bit as well on the ARC prize, a little bit on our approach on one of these videos once we get a bit further. The deadline for the competition is it's the 3rd of November. So we have quite a bit of time until then, but still a lot more progress to make if we're to get up the leaderboard. So that's pretty much it, folks. I'll chat to you next week, same time, 2 o'clock Irish time. If you want to join, probably do a bit of a longer session. Let me know in the comments if you've any questions on this, or if you've any topics you want to cover for next week. I didn't go over Simon Wilson's blog this week. I do recommend it if you want to check some news. I see there's an improved DeepSeek model out. It's 3.1, so performing a little bit better. HRM, yeah, HRM is actually good. That's on topic. I can talk about HRM next week. I do have a few things to say. HRM is there's just been um, there's just been some work to reevaluate HRM. It's a hierarchical model. It's actually related to what I talked about today on recurrent networks because HRM is a transformer model that then feeds its output back to the input multiple times. So it's got this looping, and it's a very small model that's being used to solve ARC. It's not pre-trained, so it hasn't got a lot of pre-training data. It's just trained on a very small number of ARC tasks, and it seems to perform well on ARC AGI1. It gets, I think, about 40%. On ARC AGI2, it doesn't perform well. But it's interesting, I think, yeah, to think about it in terms of the recurrent nets, and also to think about it and whether it brings an advantage over transformers, really. So yeah, there's this. Let me just quickly share my screen here. Share my entire screen. So if you go to arcprice.org, by the way, you can check out some of the prices. If you don't know what ARC is, you can go take a look at some of these. Like here's an input, it gets mapped to an output. Here's an input, it gets mapped to an output, input, output. There's a pattern here. Basically, this whole pattern is being mapped onto this part here. Then it's mapped onto this. Then it's mapped onto this. Then it's mapped onto this. And you have to reproduce the output here. Let's see if I can actually do it. Yeah, I need some orange. So this square here, I'm going to put it in here. I'm going to put it in here. Did I do that wrong? I'm going to put it in here. I'm going to put it in here, top one as well. And this one. Sometimes you have to fill out multiple outputs, but here it looks like you don't. And then you can submit. Where do I submit? Here. Okay, great. I got that right. So these are the examples that you have to solve. This is from ArcAGI1, so it's an easier one. It's actually from the training set, which is even easier. But if you go to the harder ArcEval ones, these ones are more difficult to solve. And yeah, this is what you're solving, but you have to solve them programmatically without seeing the task. It's just your program or your neural net that's able to see it. I'll talk more about it in the experience of submitting next week. But HRM, anyway, that's what I wanted to say. If you go to the blog, you'll see that that's ArcAGI3. There are some comments here on HRM. And yeah, HRM does fairly well on ArcAGI1. You can see that the cost per task is reasonably good, and it scores about 30 to 40%. It does not do well on ArcAGI2, though. It just scores 1% or 2%. But yeah, one interesting thing is they took the HRM approach, which is also hierarchical. It's two transformers, a big one, and no, two small ones. And they took both of those out and replaced it with one transformer and basically found that it performed pretty much the same. So the fact that it's hierarchical doesn't really seem to make much difference. The fact that it's recurrent does seem to make a big improvement. You can see here, if you look at doing one loop versus two loops, this is recurrent, you get a big boost in performance. Here, one loop, two loop of refinements. So the loops are definitely helping. But yeah, you might ask, well, if you just had a transformer with twice the number of layers, maybe that would perform as well as just a transformer that's looping. So yeah, there's still some kind of open questions there. Okie doke. That's it, folks, for this week. Cheers for joining.